Welcome, everyone. My name is Jim Olsta, and I am the session chair of this group of presentations. This session is titled Environmental. A couple of things to note before we start these presentations. You will have the opportunity to ask questions during this on-demand session by clicking the Questions button at the bottom of the video window. Your question will be sent to the presenter to answer as soon as they are able. To claim PDH credits for this session and any other education session, you simply need to click on the Claim Credit button on the conference homepage. From there, you will fill out the survey for any sessions that you attend. Please note that you will need to include the verification code shown in this session to verify that you did attend this session and ensure that you receive the proper credits. Please enjoy the presentations. Thank you.
Hello everyone, my name is Kuo Tian from George Mason University. Today, I will share my research with you regarding the hydraulic conductivity of bentonite polymer gel synthetic liner to cold combustion product leaches. EPA required a cold combustion product disposal facility to have a composite liner system, including a layer of gel membrane overlying by a layer of compaction clay liner. Above it, there will be a leachate collection system try to pump and collect the leachate to prevent any potential leaking from the disposal facilities to the surrounding environment. The right side shows a theoretical drawing of the sketch of the composite liner system. Gel synthetic clay liner can be used as an alternative to replace CCL layers. Because GCL is very thin, can save a lot of airspace or waste. Also, the GCL is very easy to be constructed. Especially for the area where it has poor clay resources, the GCL can be a sustainable alternative. The GCL is include a layer of sodium bentonite sandwiched between two layers of gel textile. And the traditional sodium bentonite GCL has some limitation when exposed to aggressive leachate. For example, the leachate has high ionic strength or lower RMD and high pH condition. This will inhibit the swelling of the bentonite, resulting in high hydraulic conductivity. So I will explain this concept in the following a few slides. So this slide, we will introduce the chemical indicators of the leachate. Previous researchers has identified three main parameters that affect the sodium bentonite GCL performance. The first one, called ionic strength, which is related to the salinity of the leachate. Higher the salinity, the higher the ionic strength it is. The second one is called relatively abundant of monovalent cation versus polyvalent cations, short for RMD. This is used to describe whether the leachates predominantly contain monovalent cation or divalent or trivalent cations. The research has been shows the GCL exposed to polyvalent cation while has lower swelling value, which potentially result in high hydraulic conductivity. The third one is pH. When it goes to extreme pH condition, it also affects the performance of GCL. The right side shows a figure summarizes the leachate characteristic based on ionic strength versus RMD. In this figure, we have three types of leachate, including about MSW leachate, low-level reductive waste leachate, as well as CCP leachate. So across the board, you can see the red dot represents CCP leachate, tend to have aggressive ionic strength, very high, can be higher than 1000 millimolar, and the RMD value is all over the range, ranging from like 10 to -3 all the way go to 10 to power of 2. So it's across the board. This slide showing the hydroconductivity of sodium bentonite versus the swell index. Free swell has been identified as a quick indicator test to predict hydroconductivity of sodium bentonite GCl. As you can see the right side, there is a photo showing the sodium bentonite powder in the first graduate cylinder is dry powder. The second is when the dry powder swell in DI water. The third one is the powder swell in the CCP leachate. As you can see from dry powder exposed to DI water, the swell can become roughly about 30 milliliter. Whereas when it's exposed to CCP leachate, the swelling is roughly about 5 millimeter per 2 gram. So as you can see, the swelling of bentonite is very sensitive. And the left figure showing a hydroconductivity of sodium bentonite GCl as a function of free swell value. As you can see, from the low swelling all the way increase to high swelling value, the hydroconductivity gradually decrease. Roughly speaking, when the swelling higher than 16 will have a promised low hydroconductivity of sodium bentonite GCl to different type of leachate. However, as you saw in the previous slides, when the swelling of sodium bentonite becoming very low, the GCl can becoming very permeable. So to improve the chemical compatibility of traditional sodium bentonite GCl, tremendous research has been studied about polymer modified GCl. Here we name it bentonite polymer composite GCl. And one mechanism that's proposed to govern the BP-GCl performance is the polymer clogging mechanism. As you can see in the right figure, this is a freeze-dry image obtained from Tian et al. 2016. In this figure, you can see the polymer hydrogel is connect the bentonite cluster and the hydration stage. In this stage, you can envision if there is a gap between the bentonite particles, the polymer can occupy the gap and absorb water to clogging the flow channel for liquid. As a result, the hydroconductivity of this BP composite can maintain low even when the swelling of bentonite is constrained. The left figure shows the hydroconductivity of BP-GCl as a function of polymer loading to different type of leachate. I group the leachate based on ion strength. It can be less than 200 millimolar, all the way can be higher than 500 millimolar. In general, we see a trend as the polymer loading increase in the BP-GCl, the hydroconductivity can maintain in a lower than 10 to negative 10 meters per second, and the permissible polymer loading is roughly about 5%. When the BP-GCl have polymer loading higher than 5%, it can manage the leachate in between 200 millimolar to 500 millimolar. Higher than 500 millimolar can be challenged, but it is still manageable if the GCl has enough polymer. For example, here you can see when the polymer loading go to 28%, the GCl can manage leachate has any stress larger than 500 millimolar. Back to the topic of my study, the first step that I conducted research is to compile the CCP leachate database. So the right figure shows the compiled result as a function of ion strength versus RMD. So the leachate was collected from more than 130 CCP disposal sites and compiled, and include a different type of ash. For example, bottom ash, fly ash, and FGD material, all different type of ash. And based on the leachate data, we categorize the leachate based on the major cation and anion, as well as ion strength, RMD, and anion ratio. In the right figure, you can see the ion strength of the CCP leachate can be very dilute, about like a few millimolar, all the way as high as more than 4,000 millimolar. So it can be becoming very aggressive. For this study, we focus about the effect of FGD Liche on the performance of BPGCL. Here, as you see from the figure, the blue circle represent the CCP Liche from the FGD solid disposal facilities. You can see the FGDs tend to behave on the aggressive side, and the red triangular represent the geometric mean of the FGD Liche, which is used to create synthetic Liche in this study to chemically represent the FGD Liche. The Liche recipe has been shown in the table. The ion strength of this Liche is about 473 millimolar, and RMD is about 0.65. And the major cations in this study is sodium, and the major divalent cation is magnesium. And you can see the major anion include both chloride and sulfate. The pH is set at 6.5, which is close to neutral. 3 GCl has been used in this study, include 1 sodium bentonite GCl and 2 BPGCl. The 2 BPGCl has 0.5 polymer loading and 5.5 polymer loading, so it's named BP 0.5 or BP 5.5. The red figure shows the grain size distribution of the bentonite or bentonite polymer composite from the 3 GCLs. As you can see, the grain size distribution is very close to each other, indicate the particle size in the 3 GCl are very similar. A hydraulic conductivity test were conducted in this study mainly follow the ASTM D6766. We're using the flexible wall parameters and using falling head test and constant tailwater method. The test was initially set at 20 kPa pressure and until reaching chemical and hydraulic equilibrium. And then the confining stress was increased to 100, 250, and 500 kPa to mimic the stress induced by the waste body. So we want to mimic the real field condition. This slide shows the temporal behavior of BP 0.5 GCl to TFGD Liche. The left figure shows the hydroconductivity as well as Q out versus Q in. The right figure shows the pH and EC value, the ratio between pH out versus pH in, which used to determine the chemical equilibrium. So the left, first of all, let's look at the hydroconductivity. When the confining stress is at 20 kPa, the hydroconductivity is the GCl is very permeable, ranging around 10 to negative 7 meters per second. As the confining stress increases, the hydroconductivity gradually decreases, and when the confining stress was about 250 kPa, the hydroconductivity was decreased lower than 10 to negative 10 meters per second. When the stress keeps increasing, the hydroconductivity further decreased to around 10 to negative 12 range. As you can see, we point out a circle, point out like a polymer clogging occurred when the confining stress increased to 250 kPa, which you can see the hydroconductivity gradually decrease, but after we removed clogging in the effluent, the hydroconductivity went back to the original level around 10 to negative 10 range. The red figure shows the chemical equilibrium determination. When the pH out versus pH in fall into 1 plus and minus 10% error, we call it the test run into the chemical equilibrium. As in this figure, we can see with pH becoming roughly around 12 ppf, the hydroconductivity test was reaching the chemical equilibrium stage. The EC out versus EC in fall into this range a little bit early is about 6 ppf. So in this test, after the pH and EC both agreed that of the effluent value, agreed the influent value, then we increase stress from 20 to 100 and moving forward to 250 and 500 kPa. This slide compares the hydroconductivity of 3GCl at 20 kPa cell pressure or confining stress to DI water and TFGD leachate. First of all, you can see when it permeates with DI water at 20 kPa pressure, all 3GCl maintain a low hydroconductivity. However, when the GCl exposed to TFGD leachate, as you can see for sodium bentonite GCl as well as the BP.5 GCl, they both show a very permeable, the GCl becoming very permeable when exposed to TFGD leachate. On the other hand, for the BP5.5 GCl, which has higher polymer loading, you can see the GCl can maintain the low hydroconductivity to TFGD leachate, which indicates that this GCl can be used to manage this TFGD leachate. This slide shows the hydroconductivity of GCl to TFGD leachate as a function of effective confining stress. Thus, as you can see, we have all three GCl data here. First of all, let's look at the sodium bentonite GCl. At 20 kPa, the sodium bentonite GCl had hydroconductivity about 3 times 10 to negative 7 meters per second. As the confining stress increased, the GCl had roughly about 2 order of magnitude decrease in hydroconductivity, ends up around 5 times 10 to negative 9 meters per second, but is still higher than the threshold value, which is 10 to negative 10 meters per second. In contrast, if we focus about BP.5 GCl, as you can see, the BP.5 GCl had similar hydroconductivity in comparison with sodium bentonite GCl at 20 kPa cell pressure. But as the stress keep increasing, we do see that the BP.5 GCl has a faster decrease trend in comparison with sodium bentonite GCl. When it's becoming 250 effective stress, you can see the hydroconductivity of BP.5 GCl is lower than 10 to negative 10 meters per second. This shows that the beneficial effect of effective stress on the hydroconductivity is significantly for polymer GCl than sodium bentonite GCl. We are working on this to evaluate the underlying mechanism why the beneficial effect of BP-GCl is significant than the sodium bentonite GCl. Study is ongoing. And in terms of BP.5.5 GCl, as you can see, even at 20 kPa, it's maintain a low hydroconductivity. Increase the stress, yes, has some beneficial effect, but the level is limited. In conclusion, this study has been evaluated about the 3 types of GCl to TFGD leachates. As you can see, we do observe that the BP-GCl can maintain low hydroconductivity in comparison with sodium bentonite GCl. In addition, if we increase confining stress, we do observe a decrease in the hydroconductivity of GCLs. But the BP-GCl had a significant faster decrease trend of hydroconductivity in comparison with sodium bentonite GCl. Further study is ongoing to evaluate the underlying mechanism. And additionally, we do observe that if BP-GCl with sufficient polymer loading, it can maintain the hydroconductivity even at low confining stress condition, which is a good sign that the BP-GCl with sufficient polymer can be used to manage aggressive leaches from CCP disposal facilities. This study has been financially supported by the Environmental Research and Education Foundation, and also Cytical Mineral Technology Institution provide the material test for our test for free. So I want to acknowledge their contribution.
Welcome everybody, this is Javier Paez from Atterfield Geomembrane Group. First of all, we would like to thank you, Geosynthetic Conference, to let us stay here with you in this online version, showing our research. I will present our technical paper made by Atterfield Technical Department, New Geomembranes for Challenging Containment Applications formulations for site-specific chemistry and environmental conditions. The scope of this research is to present new geomembrane technologies and a new approach for challenging containment applications. We are going to see how we can ensure the service life of a geomembrane in extreme site conditions as the one present in a mine or in a landfill by creating site-specific formulations. Our research is divided in two main sections. The first part is split in 3 points where we have done an overview of HD standards, an internal research by testing some traditional geomembranes to understand their behavior in different liquids. And after that, we have assessed how chemical solution interacts and impacts with these regular HD geomembranes. In the second part, it has been analyzed critical sites with extreme conditions as the one present in mining applications. We have created a formulated geomembrane for one specific site and assessed by performance internal test its behavior. In the last slide, we will conclude summarizing this new approach. Formulate is HD geomembrane adapted to resist in critical sites. High-density polyethylene geomembranes have been used as containment application barrier in geoenvironmental applications for more than 40 years. The first general specification available to support geomembrane engineering design was published in 1983 in USA by the National Sanitation Foundation, standard number 54. One of the most important issues was that this standard did not address the long-term performance of the material. Therefore, geomembrane industry, at the prompting of the USA Environmental Protection Agency in 1997, started working on a new HDPE specification. This finally was provided by the Geosynthetic Research Institute, GRI, with the standard GRI GM13. Since 1997, and now in its 15th revision, the GRI GM13 standard for HDPE is used and adopted throughout the industry by specifiers and government regulatory bodies. However, the fundamental GRI GM13 aim was directed towards product manufacturing quality control, MQC. It was not intended to consider site-specific design conditions. Even in the specs, states that this specification represents manufacturing quality control MQC in the clause 1.3. The initial performance evaluating testing prescribed by GRI GM13 consider OIT standard OIT and HP OIT tests as an aider or requirements. The purpose of including these two tests was to provide the manufacturers an option to choose the appropriate test method to evaluate their specific antioxidant packages. The recommended values were based on different geomembrane historic life, but not intended to consider site-specific conditions. Here in the second part, you can see that in the clause 1.4, also the GRI states this standard specification is intended to ensure good quality and performance of HDPE geomembranes in general application, but is possible not adequate for the complete specification in a specific situation. In view of this summary, GRI GM13 may be viewed as a minimum benchmark measure to evaluate geomembrane performance in low-risk containment application. For sure, is good for general applications where the project's leachate in contact and exposure condition would be relatively inert. In Atterfield Lab, we have done a research to understand how will behave a regular traditional geomembrane in different liquids. In order to evaluate that, we have created 2 samples of a regular HD geomembranes that meets GRI GM13 requirements with 2 different liquids environments taken directly from 2 landfills, one alkaline and the other one acidic. by setting at the same time 3 immersions in those liquors with different temperatures, have been obtained a lifetime extrapolations, reproducing their stage A prediction lifetime in these environments. Analyzing the table results, it can be seen that pH incubation significantly impacts geomembrane life. Both immersions, even at low temperatures, the lifetime prediction is considerably lower than in ambient environment. In addition, it can be clearly observed how the liner behaves differently in each liquor. It shows a significant impact of the acid liquors on the geomembrane lifetime in comparison with the alkaline one. Moreover, it can be observed how the influence of temperature affects significantly above 70 degrees, equaling the lifetime prediction from this temperature onward. Given these results shown, a deeper research has been done to understand the behavior of a standard GRI GM13 geomembrane in acidic solution. We have incubated 2 samples of a regular HDPE in a pot with a highly aggressive acid liquors with pH close to 1 at 80 degrees and 100 degrees. The 2 coupons were monitored by periodically removed and evaluating their antioxidant package by standard OIT and HPOIT tests. The 2 graphs show the result obtained. Analyzing the first graph, it can be observed that after 13 weeks of immersion, the GRI GM13 geomembrane, the antioxidant package is already consumed, starting the induction period to onset of degradation. The results show how in the first 2 weeks both OIT tests steep drops. In 4 weeks, the standard OIT is already not detecting any antioxidant package. The second graph shows after only 2 weeks of immersion at 100 degrees, the antioxidants of the geomembrane are already consumed. The results clearly show the high impact of the combination of acid liquors and high temperatures on a regular geomembrane. In base of this research and the consequently risk involved, a new approach to geomembrane formulation is felt to be necessary in order to evaluate correctly the service life of a geomembrane in this critical condition. An initial aspect to take into account in a lining design is the chemical resistance. Geomembrane HD normally is chosen because of it in comparison with other polyolefins. This normally is based on chemical resistance charts. These tables would be generally reliable, but there are many situations where specific testing is required and further assessment is needed. These tables only evaluate interaction between pure resin and chemicals. Antioxidant package interaction with chemical components are not evaluated. They do not consider projects with no single chemical components or with changes of the chemical composition over the life of the project. Also, long-term properties are not evaluated. In critical projects, the chemical conditions should be clearly identified. Geomembrane should be adapted to the conditions. Specific performance tests are needed to ensure lifetime of the geomembrane in these situations. In the following section, it is analyzed how the chemical solution affect to the HD geomembrane recipes and how we can adapt the formulas to resist it. Acid and alkaline solution we have already assessed in the previous slides with regular HD formulations. They would impact on geomembrane additive packages. Special antioxidants that resist better basics and acid solution can be included to reduce their effect. Liquors that contain transitional metals accelerate the oxidation process by a catalytic reaction. Hence, the durability of the geomembrane will be affected. Special recipes can be made to reduce the effect of these transition metals. Solution which includes extremely reactive and strong oxidizing agents, elements such as chlorine, will show reduction on the standard and HPOIT. In order to minimize this effect, a high antioxidant package should be present in the geomembrane. Also, solution with high in-service temperature in addition to aggressive chemicals, as we have seen before, would impact severely in the antioxidant package, with both standard and HPOID that would show a decrease. The solution for that would be the use of specific types of antioxidants with higher molecular weight and specific HDPE resins that will help better to permanent exposure to high temperature. Environmental impacts made by chemicals emitted from mining processes is a major concern in mining industry. As a result, the need for high-performance mining systems have become a critical issue to face in the mining sector. HD geomembrane has emerged as a key component to address this demand as barrier containment of process solutions after being proven of its relatively well behavior. However, as these geomembranes should face extreme conditions not present in any other containment application, a complete and deep analysis should be taken by designers to understand and specify the most suitable geomembranes. In our research, not only is analyzed this impact directly on HD typical formulations, but also it is proposed how to adapt the geomembrane formulation to create bespoke geomembranes after a complete site-specific assessment. To accomplish that, it has been selected and assessed two types of mines, aluminum and gold mines. In the slide, you can see the summary of the site-specific conditions assessment. Bauxite residue generates liquors with highly alkaline pH leachate, high sodium concentration, as well as elevated temperature of cooling water. And then gold mines generate acid liquors and can also generate another type of leachate by gold processing, which with elevated chloride and sulfate salinity with moderate to strongly alkaline solutions. Traditional formulation will not resist these extreme conditions. As such, these critical sites calls for geomembrane HD formulations with specific HDPE resins and specific antioxidants to ensure long-term performance to be able to resist project conditions. In our lab for this paper, we have created a formulated HD geomembrane for a site that the liner will be in contact directly and permanently with high acid liquid, similar condition to the one presented in a gold mine. It has been formulated a geomembrane with high quality resin, high amount of antioxidant, specific ones resistant to acid environments, and with high molecular weight. In contact with acid, a regular geomembrane will show a steep drop in their antioxidant package. The result of this formulated geomembrane incubated in high concentration of sulfuric acid with pH close to 1 at 20, 60, and 85 degrees are shown in the two graphs. First graph shows that after almost 60 days of immersion in acid liquors at 20 degrees, 60, and 85 degrees, the site-specific formulated HD geomembrane has retained more than 80% of their HPOID, not showing any steep drop. Second graph showed that after almost 60 days of immersion in acid liquids at 20 degrees has retained more than 90%, at 70 degrees more than 65%, and at 85 degrees more than 40% of their standard OID. It shows a drop in the first 30 days, essentially at 85 degrees, and then it remains. These results show the impressive behavior of these formulated geomembranes in direct contact with this highly acid environment at even high temperatures. After almost 2 months on this immersion, the formulated geomembrane's antioxidant package is not consumed yet, not starting the induction period to onset of degradation. The results do not show the typical steep drop in their antioxidant package that a regular geomembrane will present in this environment, as we have seen before, providing that a geomembrane, well formulated for a specific site extreme conditions, can be ensuring for long-term performance, minimizing the site risk by creating and customizing the most suitable geomembrane for the project needs. As we have seen in this paper for challenging site, a new approach in terms of specifying HD geomembrane is felt to be necessary. Traditional GRI GM13 standard geomembranes, whilst being an excellent general purpose specification, would be inadequate in projects where the leachate in contact is very aggressive, as mining processing and some landfills. To ensure long-term performance of this site's geomembrane, it is very important to identify site conditions and adapt geomembranes formulations, understanding how resin and antioxidant package interact with each other and with the environment that are in contact with. To do so in critical sites, we have to engage with experts, designers, polymer experts, and demand from manufacturer expertise. Pre-screened set of liners under site conditions. The new approach for challenging projects have to be able to correlate key longevity measures with new accelerated methods by short and long-term immersion testing. This new approach calls for site-specific geomembrane HD formulations that will add real geomembrane guarantee in critical sites, providing geomembrane performance in the entire project lifetime, providing real geomembrane longevity linked to ambient conditions. And finally, and most important, reducing risk to minimum, reducing any environmental, public health, and economy impact that a geomembrane failure could cause in critical sites. Thank you for your time and interest. Please do not hesitate to contact us if you've got any further question. Stay safe.
Hello all. Welcome to the virtual Geosynthetics conference. My name is Rohit Sati. I'm the Technical Product Manager with the Layfield Group based out of Canada. Today I have with me my co-author, Mr. David Beaumier. He is the Director of Geosynthetics Testing. He is with Sagios, part of the CTT Group, also based in Canada. So today we are going to present a study that we performed on stress cracking resistance of a bimodal polyethylene HDPE geomembrane. And we also compared the material to a standard grade HDPE and to a linear low density polyethylene geomembrane, which are the most commonly used materials in the industry right now. So let's get into the presentation. So we are going to cover some background information about stress crack resistance and its impact on materials. We are going to talk about the bimodal polyethylene resin technology. We have done a ton of research on this subject, so we just want to talk briefly about what molecular weight distribution looks like for a bimodal polyethylene resin when compared to a unimodal resin. Then I'll pass on this presentation to David, who is going to talk about the stress crack testing that we have performed, and also the results and discussion section. And then we'll conclude this presentation by some comments and some concluding remarks. So with regards to background, polyethylenes, and especially HDPE, can fail through a mechanism called environmental stress cracking. And the picture on the right shows you a classic example of stress crack resistance, where you can see it initiates very close to extrusion weld and goes all the way to the top of the slope. And as you can see, the branching is also evident from the parent crack. Now, stress crack resistance for standard grade HDPE geomembranes, which are mostly unimodal resins, are very well documented. Now, GRI GM13 requires a minimum 500 hours. But if I take you back to about 20 years, even longer, actually, about 30 years, early 90s, where researchers began to look at this resin and try to improve, the properties, the mechanical properties, and especially the stress crack resistance, because the more stiff the material is, you have problems with environmental stress cracking. So the researchers came up with new technologies, new additives, and finally decided to slightly lower the density of this material. And that's why they're technically medium density polyethylene resins that provided better stress crack resistance in these materials. The density was around 0.94 grams per cubic centimeters. The bimodal resin we're going to talk about today is a true high density polyethylene material with a density close to 0.95 grams per cubic centimeters. So most stress crack resistance testing on bimodal resins have been performed on pipe grade resins that are reported to have high resistance to primary exposures that led to failures in high performance polyethylene piping applications. Now, some of those notable material properties, for the pipe manufacturers include slow crack growth, rapid crack growth, and also resistance to defects and external damage. Now, these are the properties that are performance indicators for high performance piping. Now, these tests cannot be extended as is to geomembrane applications just because it's a different product type, it's a different end use application, and also the biggest thing is manufacturing. So you have to look at the equipment capabilities to see whether that type of resin will be able to extrude through the equipment the geomembrane companies have right now. So we needed to devise our own methods to evaluate the geomembrane performance. So now looking at what are some of the factors that can induce stress cracking? So stress cracking can definitely happen at tensiles that are lower than its mechanical properties, but it can also be induced by surfactants, by elevated temperatures, and some of the other factors that can include welding, overheating during welding, and as I said, the amount of stresses. Now, there are some studies that are already out there where they have looked at heat and stuff like that that can actually induce stress cracking and can create issues to the geomembranes. So this study is basically presented by Kerry Rowe and his group on aging of HDPE geomembranes exposed to air, water, and leachate at different temperatures. So notably, if you look at the pictures in the bottom, you can see the geomembrane has been completely degraded in 85 degrees Celsius water for about 105 months. And also complete destruction is seen for geomembrane at similar temperatures, but this time it's synthetic leachate. So chemicals definitely induce microcracking and attack the polymer chain, and that can cause the rate of degradation to accelerate. So going to the next slide, I'm just going to talk about unimodal distribution versus bimodal distribution. I want to just briefly talk about the bimodal polyethylene resin technology. So when you look at a polymer being manufactured, what happens is when you analyze these molecules using a technique called gel permeation chromatography, you see a distribution of these chain lengths, as you can see on the picture. So you got on x-axis the molecular weight, on y-axis you have the weight fraction. Here you're seeing actually a narrow distribution curve, so where you can actually achieve average properties in your material.
So you can have average tensile properties, average long-term endurance properties. Now, if you try to narrow it further, what you'll get is you'll get actually stiff, higher tensile material, but then you will have difficulty extruding the material. You may have also difficulty with achieving some of the long-term endurance properties. Now, if you try to widen and shorten the curve, it could be a supple, soft material, but then you are actually compromising on other properties like strength and stuff like that. So to address some of those concerns, industry has been looking at bimodal resin technology. So instead of unimodal, it uses a two-step process. So that's why you see actually two peaks, and here you can actually see a wider molecular weight distribution, which can also provide you with higher tensiles, and also does not compromise on long-term endurance properties like stress crack behavior. And that's what this whole testing is all about. Bimodal resin technology also helps with the tie molecules. So now what you are seeing here is initial steps in deformation of polyethylenes. And you can clearly see that the higher number of tie molecules, the stronger the product is, the better the crystallinity and the overall chemical resistance. Over to you, David, who is going to talk about the NCTL testing.
Thank you very much, Rit. So I will just switch to next slide. Sorry. Okay, so if we get then to what is the testing for stress cracking in the world of the geomembranes, we want to look at NCTL, which stands for Notch Constant Tensile Load Testing. This is a test that was developed in the 90s and defined by ASTM D5397. The test consists of submitting a very small dog bones with a small notch in the narrow section and immersing it in a bath that contains a solution of 10% IgPol CO6030. And we then apply a load, so it's the specimen and is subjected to tensile loads. And what we want to look at during this test is the time to stress crack propagation in polyethylene, and there will be then a time that to failure that will be measured because each of these little arms are connected to a timer, and the objective herein is to determine a complete NCTL, and this consists of testing the material under different load range, on a wide load range. I mean, from 28% to 65% of the yield strength. And the reason for this is that we want to look at how the material will behave under its stress at yield point. So basically, we don't want to look too much on how the material is behaving in the ductile behavior, but more likely in a brittle mode of failure, which is way below its yield stress. Its yield strength. And the first thing first, we will want to measure what is the yield strength of the material, and we do that by doing a standard tensile testing, and we will then look at precisely what is the tensile strength of each materials. And in this close-up, you may see that we have a quite different behavior if we are looking at LLDPE, HDP, or HDPRT, which is this bimodal polyethylene. And the reason for this is much related to the level of crystallinity of each materials. and also their molecular structure. So first, the classic way of looking at it is to look at the load in terms of percent of each material yield strength with failure time. So we can then determine what is the envelope of rupture of each material. Basically, the higher loads are more likely simulating a ductile behavior or ductile failure up to a point where we will reach a ductile to brittle transition zone. And this is the one that is circled in red on this picture. And we may see at this point, even if the PERT was below in terms of yield strength, percent yield strength, we will get to a point where it's both HDP, the conventional or HDP for geomembranes, and the new developed PERT are quite close. And what we will see on the next picture, if looking at it in terms of load, in terms of PSI versus failure time, is that at this point we will get both materials about in the same region, but leading to different time to failure after time. Subjecting it to lower loads, for instance. And this brought us some questioning about the behavior that we will try to answer on the following slides. First, we looked at what were the micrographs on the facies of rupture of each materials. Well, first thing, the LLDP showed likely a more ductile type of facies of rupture, and we may say that because of the wavy surface, elongated. Well, I mean, from these wavy surfaces are often related to a elongation on the surface of the material, and if we get to even lower loads, we get always this type of wavy surface and ductile mode of failure in all LLDP samples analyzed after their stress crack tests. Okay, so in overall, what we can get on conclusion for LLDPs is that overall the mode of rupture was all ductile in any cases. Then if we look at HDPE, well, we will get at first wavy type of failures, which as I told previously, related to ductile type of failure. As we go through, we will get a little bit different type of morphology. Even this one is still ductile, because we will see what gets to be a real stress cracking initiation on this picture, where we can clearly see some little peaks close to the limit of this notch on the top of the picture. And this is how this stress cracking is first initiated. And after a certain time where it hasn't propagated to a certain point, it gets back on the bottom of the image to a ductile mode of failure at the end. But all this is basically initiated from stress cracking, a brittle type of stress cracking. And looking at this typical HDPE behavior, well, we can see that this ductile to brittle transition will happen in the region of a bit over 1000 psi, and at a time that will be between 500 hours to 1000 hours. exposure in this test D5397. If we then look at how this bimodal PERT is behaving, basically we still get these type of ductile failures at high loads, up to a point where we get a little bit over 1,000 hours and a little bit over 1,000 psi. As for the HDPE, we get this type of brittle failures. But the main difference is that you don't have this elbow as what we had previously with HDPE, and that is well documented in the literature. But it's basically the points are likely aligned with what we observed in the ductile behavior, and this leads to a maybe more predictable brittle behavior of this PERT HDPE. So now I will let the presentation to Rohit to finish on this subject.
Oh, thank you. Thank you, David, for the interesting results. So as you know, the MDP geomembranes have served very well for a number of years, but they're occasionally challenged with demanding applications, and we have all seen that over the years. And that's because of the lower density, that has led to slightly lower tensile strengths and of course lower chemical resistance. Now, this coming to this study, the higher tensile resistance of this specific bimodal resin resulted in higher resistance in the ductile failure mode than standard HDPE. But moreover, its stress cracking resistance behavior was found without any clear transition of the failure envelope from a ductile to a brittle behavior, which gave us actually longer time to reach the ductile brittle transition, as well as higher stress crack resistance when compared to a standard grade HDPE or MDPE material. Our results are also very consistent with some of the previous studies that have been done on this material. This is the fifth paper, in a series of papers that we wrote on this material, beginning in 2016, I think. Our research started in 2015, so it's over 5 years now that we have spent a lot of time in testing on this material. So whether it's tensile, whether it's long-term performance, under elevated temperatures, or with strong oxidizers like chlorine. So we have done all of that, and we are really proud to have recently received the top 100 R&D finalists award. So Layfield, along with the resin supplier Dow, we were we presented our entry heat guard high performance geomembranes, extending lifetimes and performance of groundwater protection infrastructure through materials and innovation. So very, very proud to have received this this prestigious award. Next slide. So thank you everyone for listening to our presentation. So you can post your questions here, or you can send us an email at at the email presented below. Again, thank you so much for your time. Have a great day.